All right, good. And then with that, it's my pleasure to introduce Naomi Nickerson from PsiQuantum. She will tell us about photons with the ZX calculus.
Thanks very much. So yeah, it's great to be here. And I think this maybe leads on quite nicely from some of the things that Steve might be talking about. This morning, I want to talk a bit about actually two aspects, two sort of mathematical tools that are things that are useful in the design of quantum error correction in this regime that we're kind of all here to talk about of hardware-focused error correction. So this is based on a couple of papers with a whole bunch of my colleagues at PsiQuantum, and I'll highlight sort of who did what as we go through. So yeah, as I was introduced, I'm at PsiQuantum. PsiQuantum, we're based sort of down the other end of the bay, working on photonic quantum computing. So I've been at PsiQuantum for about 7 years, and I joined with a kind of view to figure out really how do we do actual quantum error correction using photonic qubits. And so this is just some kind of a map of the type of things that people are thinking about. We've got component design with to process and manipulate photonic information on silicon chips. These chips get compiled into larger packages and systems, and ultimately we're designing these systems to build quantum error corrected qubits and do computation. And so, you know, starting this project a bunch of years ago with the goal of designing this kind of a thing, which is maybe the background that we all come from. So, you know, 20, 30 years ago, this was the only picture of quantum error correction. And these are really, you know, beautiful, simple, clean mathematical models. Topological codes, there's a reason that many of us like them so much, because there's a like real beauty in the math that lies underneath these things. They're really appealing. They're of interest, even aside from quantum error correction. But when you're faced with this challenge, as I suspect a bunch of people here have looked at that, where we want to take a physical system and figure out how to map it into that quantum error correction scheme, we're faced with two very different types of physics. So on the one side, you've got some messy physics that's describing photonic systems, so, you know, quantum optics, but with throw in a whole bunch of errors. You've got, you know, Gaussian waves describing those things. You've got line edge roughness on the chip. There's 1,000 sources of places where errors come from, and you've got some like really messy physical models for describing what's going on there. And then on the right-hand side, we have where we want to get to, which are these, you know, topological codes. And the place you end up when you try and do that modeling, and people have been doing this, I've you know, since my PhD have been doing this kind of work, is you end up building error models that just look something like this. So you're forced to just large maps of numbers, like density matrices, like I can simulate with errors or photonic qubits with errors, and it ends up like this. And this is great, and maybe it gives you the right answer, like hard to tell, but maybe we get a number out at the end. But this thing is really not very helpful if you want to do design. So a human cannot look at this and see what we should improve. Like, where do you see that there's an optimization to be made? How do you see that there's some inefficiency in this system? And so a kind of underlying theme of the work that we've been trying to do alongside designing these systems is looking for better mathematical tools, better simulation tools, something better than this that can actually allow humans to stare at these things and improve designs. And I think, yeah, when it comes to really hardware-focused models, that's still a place where there's more work to be done. So that's really the motivation of what I'm going to talk to you about in this talk, is searching for better mathematical frameworks for quantum error correction, where we're actually talking about hardware-focused models. So not, you know, just stabilizer measurements with you know, perfect measurements or some simplified thing, where we can really describe hardware level elementary operations and the errors associated with them, but with more clean mathematics. And so there are two pieces to this. It's a 30-minute talk, so I'm not going to be giving really deep dive tutorial, but hopefully I can kind of give a flavor of what the idea was behind these things, how we're using them in case these are things that are useful to anyone else here. So the first piece is based on the ZX calculus and how we can use that language to describe fault tolerance, and how that's been a really useful tool for us in looking for kind of similarities and understanding the underlying structures between different schemes. And then the second piece, fault-tolerant complexes, is specifically about topological error correction and trying to really extend this topological construction, interpretation of systems to even the case where we're starting from like elementary basic gate level operations. And before I get into that, and I feel like I've been set up very well by both Steve and Mike's talk here, which is to say that all of this error correction in the regime of real hardware, we have to basically forget about codes. Like, codes are really not the thing that we care about. We care about the fault-tolerant protocol. So by a code, we're talking about a static object. It's a kind of mathematical object, which has, if we're talking about stabilizer error correction, stabilizers. It's really not a physical thing. Like, this is some imaginary thing that we can write down on paper. When we want to implement a real system, we're always talking about a fault-tolerant protocol. So it's a sequence of physical operations that interact with physical qubits. And we build that up over multiple time steps. So we're looking at an object like the thing on the right. So this would be a surface code that's undergoing a Hadamard gate. And it's really, really helpful to think about that whole object. So not just a code and a series of time steps, but to look at the time space diagram. And yeah, Mike had a bunch of pictures of those in his talk, which I enjoyed. So yeah, there's kind of a bunch of things that have come from this line of thinking. So you can find better thresholds with surface codes type schemes by relaxing the conditions of really having 2D codes. And again, Mike did some of that work. So one of his papers there, like really pushing the geometry of these things. And you can look at logical gates in a way that makes them more efficient. And this is kind of an extension of that to how we can look at the inner workings of what's going on in fault tolerance. So yeah, first let me talk about fault tolerance with the ZX calculus. Now, it was really Fernando Pastowski and Daniel Litinsky who imported this idea into our team. And it's one of these things where it sort of started in some corner with someone rewriting schemes with the ZX calculus, and then it caught on somewhere else, and now it's just spread everywhere. And I promise I'm not here advertising for Bob Kirker, but I really do think it's a fantastic way of describing things. And I'm guessing some people here have used it because it has become very widespread in a lot of different areas of physics. But I'll give you the very basic run through. So ZX calculus is a graphical formalism for describing quantum physics. So we can use it for everything. Here I'm just going to be interested in looking at how it applies to fault tolerance. But the building blocks are very simple. It's basically just these three things. So we have some green spiders, these little green nodes with some legs sticking out. You can think of these as a kind of node in a tensor network diagram. And you can kind of think of this thing, this green one, as being a GHZ state. So a tensor network which has a GHZ state sitting on the output legs, which are qubits. Then we have a red one, which is the X equivalent, so X spiders, which you can think of as having a GHX state on the outputs. And then there's a Hadamard, which just kind of converts between these two things. And the other really important aspect of this notation that's going to be helpful for us for fault tolerance, this description of that's what's referred to as Pauli webs. And so these are, you can see in these pictures, these colored lines. So in the top row is a Z spider and a series of these colored lines that are basically representing the stabilizers of that state. So if this was a GHZ state, there would be one stabilizer that was across all of the legs of the X flavor, and then all the pairwise Z stabilizers. And so, yeah, they're represented with these colored lines that is going to allow us to see how these things connect together. And then the final piece of this, which is also what makes it a useful tool, is that there's a series of identity operations that tell you how you can change from one flavor of this representation to another. So a red spider is equivalent to a green one where I've put Hadamards all around the outside. So that's just saying that I can convert between these two flavors of state. I can take them and merge them together or split them apart, and that thing is equivalent, assuming that there's no errors. And then there are some other identity operations. If I do two Hadamards, that's an identity, and so on. So again, this is just a restatement of all of the, the normal Pauli operations that we know. So this was the super quick run through, and there's a bunch of references in those slides of like very detailed and comprehensive reviews of those things from the people who built that formalism. So now we want to take that and apply it to fault tolerance. And so the reason that this is going to be useful is that we can re-express all of the operations that we want to use to build up fault-tolerant protocols in this language. So whether that is a circuit-based model, whether it's what we work on, which is fusion-based quantum computing with photons, whether it's some other kinds of parity projections in topological qubits, you can express all of your basic building blocks in this same language. So you can see here what this would look like if I'm taking circuit level operations, so control NOT gate, Z measurement preparation, and then assembling those things into a circuit. And so you end up with a kind of series of little ZX diagrams, little elementary blocks that are describing these operations. And then, yeah, the same thing. So this doesn't have to be for circuit-based. I can construct those things for a photonic fusion measurement, which is a destructive measurement with two classical outcomes. Those are represented by the bold lines here, representing classical measurement output. Or in the case on the right, for a 2-qubit parity projection, which preserves the qubits coming out. And all of these things, they obviously look very similar. They just look like little components of ZX diagrams. So we can take those building blocks and then assemble them, rewrite, the circuits that are used to implement the surface code or whatever your favorite kind of fault tolerance is. You can take it and reconstruct that in the ZX language, and you end up with some picture that's going to look something like this. And if this thing is fault tolerant, then it's always going to have a few basic properties. So, well, the first piece is there is the protocol. So this is a description of all of the operations that are going into implementing that code. So if we were looking at a surface code with, implemented with gates, this would be representing a whole series of control NOT gates on qubits, single qubit measurements, single qubit preparations. They all end up in this network, and this is looking at kind of multiple time slices in that model. And this thing is going to have, we've got the bulk of this thing in the middle, but you can see at the top and bottom in this picture, we have a code. So there's a code at an input and then a code at the output. So there's a bunch of these tensor legs sticking out, which are representing the code at one point in time and at another point in time, or one point in space and another point in space. Okay, so the next component we're always going to see here are code stabilizers. So there will be Pauli webs. So here there are these red lines indicating the presence of these Pauli webs, these stabilizer kind of components that have come from assembling all of these different building blocks that represent the stabilizers on the input or output code. So these are webs which have some support in the bulk, but are supported on the output qubits. So if I just kind of map that thing to the output, these would be representing the stabilizers of the code. Then there are checks, so fault-tolerant checks. So these are Pauli webs that have support only inside the bulk, and these are like small closed Pauli webs. And these things are closed, and that means they're going to be providing information as I propagate through this protocol. All of the elements, all of those elementary operations that went into that check are checked by that collection of measurement data. So if something has gone wrong, I'm going to see it in the classical data that's coming from those edges. And then finally, there are logical correlators. So these will be extensive Pauli webs that transmit all the way through this system from the input code to the output code, and they go through the bulk. And these are the objects that are propagating the quantum information from the logical qubit that's going in to the one that's coming out. And so again, this is just a restatement of the properties of a fault-tolerant logical channel, but in this language of the ZX diagram. So yeah, why does this matter? I mean, I have just shown you a picture of a protocol that like everyone here knows. And the reasons are, if you're in the business of trying to do design of these schemes, trying to really understand their structure and improve them, then you get a lot from being able to look at these all in a unified language. So you can take schemes that were defined for one hardware, say take something that was defined in the circuit model for superconducting qubits, write it in this language, and then immediately transfer it to something that we can use in a photonic architecture, because we can see how to break it into these building blocks. It makes it much easier to optimize protocols because you can start to look for these equivalences. You can even automate some of those things in searching for modifications of the protocol that might perform better. And it's really useful for simulation because, again, we can write this in a like simple format and automate a lot of the processes that are going into protocols that would otherwise be very complex. And so I'll just give you a couple of examples of those things. So this first one is a spot the difference on these protocols, which you can. I'm only going to give you 5 seconds, so you're not going to have much time. But they're extremely similar. There are some different colors there going on, some different colored lines. But all of these things are essentially the same. And actually, if you use those identity operations, they're all exactly the same. And these 4 pictures are representing surface code type fault tolerance in these 4 different models of computation. So circuit-based, measurement-based computation, fusion-based computation, and a Floquet-based model. And so, you can see from this one of the reasons why this is so useful, because we can just see when we write it in this way that all of these things are actually exactly the same. They have the same underlying structure. So they're not going to be the same once you start to put errors in. Errors are going to behave differently. They'll appear at different places in this structure. But you can see that kind of underlying stabilizer construction is the same. And so you can immediately map methods between them, things like decoders or logical gates. So like, how do I do logic with Floquet codes? Well, I just write it in this way, and then I just immediately put across all the methods that we know for doing logic. I'll give you one other example. So yeah, Steve already talked about this. This is a picture from this extremely nice IBM paper from last year looking at a great way of using LDPC codes, really nice scheme. We want to look at how that looks in the photonic architecture. Daniel Latinsky, can take this, map it into a ZX diagram, use that to map it into a photonic implementation, and then Yihua Liu, who ran a simulation, and this whole process took like 1 week. So this is something which previously would have been like months-long exercise of constructing schemes and building error models and trying to understand even how the things mapped. And it just makes it so much easier to understand the translation between platforms. Okay, so let me move on to this next piece, fault-tolerant complexes. So this ZX diagram language, hopefully I've convinced you a bit that this is like really useful for looking at the structure of fault tolerance. But one thing that it doesn't include, if you're interested in topological codes, is any kind of geometric understanding of the nature of the check operators. It doesn't have that kind of topological relationship to the geometric underpinnings of where those codes are coming from. And so this was the motivation behind some of this other piece of work. So yeah, to say this kind of more explicitly, 2D surface codes, we all know these things extremely well, and you can take any tiling of 2D space and turn that into a surface code. So you put the qubits on the edges and the checks go on the vertices and the faces. And so any tiling of 2D space that I can write down, it gives me a 2D code. But what we're really interested in here is not the code, it's the protocol, a protocol that's made from these elementary operations. And the situation was basically this. We have a ton of examples. We know loads of ways that we can assemble gates together, loads of ways in fusion-based quantum computing where we can take resource states and measure them, and we end up with a surface code. But what is actually the family that's describing all of those things? These were kind of very ad hoc, and we just, you find examples. And so this was the main result of this work, is showing that if we have a 3-dimensional cell complex, then we can use that to define a whole family of these surface code protocols, really from basic operations. And the restriction is just that any 3D cell complex can represent surface code type fault tolerance if every edge has exactly 4 incident faces. So, okay, let me just, I throw out some things that are a little bit vague. So I said what we're interested in to start with is looking at surface code type fault tolerance in a protocol. So what does that mean? If we look at our protocol as this 3D object, I'm going to say this is a surface code type fault-tolerant protocol. If I can take any slice through that protocol and see that what I'm left with on that boundary is itself a surface code. So obviously this is the case if I have a surface code and I measure it over multiple time steps and I freeze at some point in time, I have a surface code. But this is saying something more, which is, there are a few conclusions I can draw from this. So yeah, if I take some slice, then I have a surface code on the boundary. It also tells you that if I take some small closed surface, so some small thing that is representing some elementary block, some small piece of this protocol, then that thing should look like a small surface code on the surface of a sphere. So this is maybe not obvious that this should be the case, but it actually turned out this was the case for all of the protocols that we knew about in fusion-based quantum computing. And so this then leads you to this definition that I gave on the first page. So if we can meet those criteria with this construction, which is a cell complex, a 3D cell complex, where every edge has 4 incident faces. So if you just meet this criteria, then every slice that I take through this system will allow me to define a surface code on that boundary. And so this object is then a complete description of a fault-tolerant protocol. It tells you, unlike the ZX diagram, where it was a little bit, you had to kind of deduce the structure of the checks. This thing contains within it a description of exactly the elementary operation. So I've got resource state here because we were looking at this originally in the context of photonics. It tells you how the things are connected together. It tells you, the construction of the resource state, so exactly a stabilizer description of, or a ZX diagram, if you like, of what the building blocks are. And you can extract from this thing the syndrome graph, the decoding graph, and everything that you'd want to know. Okay, so again, like, why does this thing matter? This is it's a kind of cleaner description of some of the physics we're already doing. And the reason that I'm interested in this is because we're continually looking for new and better fault-tolerant protocols. So as Steve was saying, we're not done. We need to find things that are better. And part of that is looking for things that have better tolerance to error or suppress error better. And this way of looking at things allows us to really automate that search from the level of basic building blocks. So we can automate the search and find a whole bunch of new examples. It's, again, really valuable as a simulation tool. And at the bottom, maybe a little more vague, but this gives you a much better understanding of where some of the properties of these fault-tolerant systems are coming from. So if you can really represent these protocols in this topological way, I can see the geometric origins of some things that I care about, like what is the degree of the decoding graph? So where are the thresholds coming from? And how does that relate to certain geometric properties of these systems? So yeah, just to look at a few more, because I showed you a cubic picture, which is extremely boring, but Yihua Liu, who ran a whole bunch of simulations using these methods from computational tiling theory that, again, it was Mike who did in some previous work in an MBQC setting. And here we could apply the same techniques to look for these fault-tolerant protocols. You can run this search, and we found more than 600 examples in just like a relatively short runtime. And there's some examples of these things here. So these are pictures of a cell complex. But these pictures, these representations, then allow us to read off everything you need to implement the protocol. So you can read off the construction of the building blocks. You can look at that as this topological picture, or in these ZX pictures. And for the work that we're doing at PsiQuantum, that means turning these things into photonic resource states and then plugging them into an architecture that we can simulate and understand the properties of. I won't say much more on this, but like the same principle, the same idea of fault-tolerant complexes can be applied to other topological codes or systems. So you can look at the same kind of models for color codes, for subsystem codes. And in both cases, that allowed us to find new instances that weren't in the literature already by running a similar kind of search or construction. So I think I'm out of time. So just to wrap up, I think the underlying principle of all of this is that what matters in the hardware-focused regime for quantum error correction is the protocol itself, not really the code. The code is really secondary. And we still need better mathematical tools to understand those hardware models, hardware error models, to enable that design and simulation so we can move faster towards systems that are really working. And yeah, I've talked about two of those things, the ZX calculus for really understanding the kind of inner structure of these schemes and mapping between models, and fault-tolerant complexes, which kind of really pushes the topological picture of error correction to a deeper level, to the level of elementary building blocks. And yeah, be great to talk about some more of these things. This is the team at PsiQuantum and quantum architecture, and a lot of these people did a lot of the work in the work that I just presented. And I'll say we're also hiring, so if you're interested, then come and talk to me after the talk. Thanks very much.
Thank you very much, Naomi, for this very nice talk. Are there questions or comments?
Yeah, okay. So when you identify that these are physical processes and not just protocols, are you pointing out that a fault, or are you suggesting, maybe if you're not, that a fault has a particular structural complex, or that it has a lack of a structural complex description? Is it just like, is a fault an absence of one of these structures?
You're talking about the fault in fault-tolerant? Or
yeah, like if you're discussing it as in terms of like actual physical existence on a circuit, can you identify from these types of approaches, or do you think you could identify for these types of approaches, that a fault should have an actual physical description, or could you even say that it has a lack of one of these types of descriptions that you've given thus far?
Yeah, so maybe I didn't say very much about what a fault actually was in these systems, or an error. So if you're looking at error correction, say with a gate model, because maybe the one that is most familiar, you have a 2-qubit gate, and there's some model which is pretty good for describing the errors, which looks at errors that happen after you apply that gate. So in other words, you can look at some kind of elementary block of this ZX diagram and say, I can treat this thing with Pauli errors that happen just at the output ports here. And so the challenge with working from, if you start with just a stabilizer error correcting code, and you use some of the simpler error models that say, well, just stabilizer flips, or just put Paulis everywhere, that's not capturing a lot of the structure. So these like hook errors that Mike was talking about, that come because I actually have errors after every single gate. So when we say fault tolerant, we're looking for ways of assembling these operations with really physical error models where, they turn into a fault-tolerant propagation in the code. So I hope that answered your question.
More questions?
Are any of these tools that you've built available to people outside of PsiQuantum? Is that open sourced, or
they're not currently?
Do you have any plans to do them?
Not currently.
Unless you follow the hiring call. Are there other questions? Yeah.
Do you have any comments on how what you just presented, this is probably an unfair question, but how what you presented can take advantage or not of the previous talk on surface code and
Of Mike's talk?
Yeah.
Yeah, okay, so I mean, there's two elements here. So one is with these fault-tolerant complexes, you're looking at different kind of internal geometric structure, and that's something which you could directly map that into the stuff that Mike was talking about, which is at the logical level. So he had pictures that used a square surface code, but you could replace the inner workings of that with a different geometric structure, so the two would pair together very well. And then with the ZX calculus, yeah, it's not obvious to me what you might find, but if you construct in a way, because this is at a logical level, another thing you can do is use the ZX calculus to describe the workings of these things at the logical level. And I didn't talk about that, but that's something we also do. So you can represent these space-time diagrams rather than like these blocks. You could represent a logical ZX structure. That's the logical circuit you want to do. And then you can look at manipulating those things. So again, I think if you write down the structure of these yoked codes in this picture, and then you look at the operations you actually have, maybe you find some ways of reconfiguring it that turns out to be more optimal.
But you might need something in addition to go between those two layers or something.
So if you have, you can, if you treat these things as being at the logical level, then you need to define what is my logical construction of these elements of ZX diagrams. And this is, I put the link in here somewhere. So this paper at the bottom on logical blocks, the idea of that is a way of constructing logical blocks that are implementing like ZX spiders, basically. So you can look at everything as turning into these elementary blocks, but that's only one way. So then there are many other ways that may be more efficient that hopefully someone will come out with that you could slot in.
I think Mike wants to comment.
Can I just make a comment about that? When we first did the yoke stuff, we went in these topological diagrams, and first we got it wrong. And then we looked at the ZX diagram, and then we looked at the ZX diagram, and then we did it right, and then we looked at the ZX diagram closer, and then we made it better. So the answer is absolutely yes. Like these ZX diagrams are like crucial for doing these optimizations. They're very, very helpful. Yeah.
I was just curious. You said you looked at the bivariate bicycle codes. Are there results available?
I don't have any of the links on that now.
Thanks.
Right. So don't see any further questions. Then let's thank Naomi again, and also all speakers of the morning session. Mike and Steve. And then let's reconvene at 1:30 for the afternoon session.